talk about what inverse variation is, let's talk about what it is not. If I have y equal to k times x, then I just see that as x would grow, so would y. Oppositely, if x were to go smaller, y would go smaller. So it's like they have a directly proportional relationship, which is different from what's going on here. So if I have x, y equal to some k, so let's just know that this would have to stay the same. So if it was 3, then it would be locked into being 3. And if I had 3 times 1 as a starter, but I wanted to increase the value of x, then the only way that that's going to stay equal to 3 is if y decreases. So that's like what an inverse relationship is. As one increases, the other decreases. And the reason that they point out this has to be non-zero is that I want you to write this a second way, and we'll solve for this really quick. xy is equal to k, but a lot of the times these are easier done if I have y by itself, because that's the whole function notation look of things. So I'm going to divide both sides by x. X goes away, and I'll have y is equal to k over x. And you can also see that written as 1 over k times x. And the reason I like this more is because it's kind of a little bit clear to me that if I make this value bigger, then I'm going to be getting a smaller result. Or if I make this smaller, which is more confusing to see, then I'm going to be getting a bigger result. But if you try things in your calculator, you see that that's what's going on. Now I'm going to do this the book's way, and then I'm going to do it my way. So we're going to graph an inverse variation. And here we have r and we have t, and that's our table of 5, 10, 15, and so on. The time that t takes to travel, the time t it takes to travel a certain distance varies inversely as the rate r at which you travel. And when you are given these problems in the book, you're thinking, okay, x, y is equal to k, or maybe I'm thinking y is equal to k over x. So that's what they mean. They're telling you that. That's like your go-to. So the equation RT equals 250 can be used to represent a person driving 250 miles, so that's the distance. Complete the table and draw a graph of the relation. So let's rewrite RT equals 250. And if I do this the book's way, I will plug in 5 for r, and I'll get 5t is equal to 250. And then to solve that, I'll divide both sides by 5, which is going to mean that t is going to be 50 hours. So my immediate reaction was like, well, that seems pretty ridiculous. And if I try to do a sanity check on it, it's like, well, no way it's going to take somebody 50 hours to drive somewhere. But if they're only going 5 miles an hour, that's pretty darn slow. Now here's my thing about this. If I wanted to keep going about it the way the book's doing it, well, then I had 10t is equal to 250, and I'd have to divide by 10 and go from there and get 25, and so on and so on and so on. Or I could say, well, let's take RT, which is my inverse relationship, is equal to 250, and well, I'm always, plugging in r, so I'm going to get r to the other side, and I'll have t is equal to 250 over r. And then now I'm not going to bother showing work for this. I'm just going to do 250 divided by 10, 15, 20, and so on. Now if you're looking at the chart and you're not sure what I've written, just make sure you do this on your own, because I've rounded the nearest tenth on this. Since it's like a table, it's going to be easier to write it that way. Now we're moving on to the graph part. Now I don't have x over here, but they give us r first, so maybe that makes more sense. But also, if I think about it, this does feel like I'm plugging something in. Now, the highest value of r is going to be 50, and the 10, 20, 30, 40 points are going to be there, and then my 5s are going to be smaller tick marks as I go. And then as I do t, I'm going to go all the way up to 50, which is really determined by my starting value here. And then I'm going to go all the way down, and I'll keep these with 40, 40, 30, 20, 10. And that'll probably be close enough. All right, you could also have done 25, a lot of choices there. Okay, when I'm 5 over, I'm all the way up to 50. But the weird thing is, when I'm 10 over, I'm halfway from 50. When I'm 15 over, I'm at like 16.7. 20 puts me at 12.5. 10, and so on. But, the neater I keep this, and now I'm turning my page. You're not seeing me do this, but it's easier for me to make a swooping movement from over here than it is if I'm starting up here and like looking at it straight on. You can ask me what I'm talking about in person. And I can see that this is going to hug the x-axis, meaning it's going to get really close, but it's never actually going to cross the x-axis. And that's because I'm infinitely dividing it by larger and larger and larger numbers. And this is a really cool relationship. But yeah, we've talked a little bit about this probably in class with the Netflix math problem I do. Graph an inverse variation equation in which y varies inversely as x when y equals 12 and when x equals 4. This is definitely frustrating in terms of the language. So that is not even how you write language. That is kind of. So you know that I know that we have this formula, x, y equals k. And if they tell me when y is 12 and when x is 4, then I can plug this in to figure out that k would be 48. And optionally over here, if you want to show this a second way, y equals k over x, and then I would have 12 is equal to mystery number k over 4, and then you could solve that and figure out that k is 48. So, there it's where like maybe that's why they show you the xy equals k approach, because it's easier to grab k from this. But now we're told to graph it. So this is where I would say this is easier. So if xy is equal to 48, I'm going to have a heck of an easier time solving for y and then doing 48 over x. Now, I think about plugging in 1, and maybe I'll build a table for these early on ones. X, y, and let's think about what values would make sense. Well, if I plug in 0, I want you to write UND, which would be a shortened version of undefined, because I can't divide by 0. But then if I were to put 1 in there, I would get 48. 2, I would get 24. And here I'm just looking over there and dividing by 2. 3, well, that's kind of ugly, so I'll, in my calculator, type 48 divided by 3. And I get 16. Not so ugly anymore, actually. Whoops. And then over here I'll get 12, and then 5 is a terrible number that I wrote poorly. And 48 divided by 5 gives me 9.6. Now, I'm getting closer and closer to the x-axis. I don't think you need to get out of control with how many points you graph. So here I go. 5 all the way over there. 1, 2, 3, 4. And then I got up to 50 here. 25 would be half. And I'll just be a little bit of a corner cutter on this one. So catch up to me and then do your best to make a neat graph. Now you also could plot negative values here. So I'll sketch this, and you can pull open GeoGebra for a moment if you'd like, and you can actually type in y equals k over x and create a slider from that and manipulate it and see what happens with the graphs here. See what happens when you make it negative. Watch as it moves closer and then further from the origin. And that would actually be worth your time. Okay, I think that you can make this an OYO problem, and this an OYO problem. And let's look at that language really quick. They're saying graph an inverse variation. So you know that you're going to be dividing. That's what makes it an inverse. So as I try to process the meaning of those directions, so y varies inversely as x. That means that y is going to vary. It depends on x, but in terms of this whole division thing. And then they give me this specific value so that I can figure out what k is. We'll hang tight on moving into these types of problems for a second video.